which I'm sure is going to be great. I'm happy to introduce you Nicolas Sanhueza Matamala from Universidad de Concepción, and he's going to talk about a hypergraph bandwidth theorem.
Okay. Thank you. Thank you for the introduction, for the invitation to all the organizers. It's been a very fun week. Everything I'm going to say here is joint work with Richard Lang, who is now in Barcelona. Okay, so I will begin talking about graphs, blobs, bandwidth. And my starting point here is this very basic notion from extremal graph theory, which is the extremal number. So if you have a graph H, we can define the extremal number, which is the maximum number of edges which a graph can have without having a copy of H. And there's a general phenomenon where you can say that if a graph has many copies of a graph H, not only you get many copies of H, we also get more complicated structures which are related to the shape of H. So you have these very trivial observations. If you have strictly more edges than the extremal number, you have one copy of H, of course. But then, if you have a little bit more, let's say a quadratic number of edges more than the extremal number, not only you get a copy of H, you get many copies of H, and they are clumped together in a very funny way. You get this T blow-up of H. This is what is known as this phenomenon of supersaturation and proved by Erderstone. And what you get is essentially this. So if you are a little bit above the extremal number for the triangle, not only you get many triangles, but your triangles do something like this. So you get a copy of this graph, which is obtained from the triangle by kind of substituting every vertex for many vertices and substituting every edge for a complete bipartite graph between those edges. Okay? So not only many copies, but copies doing this kind of blow-up shape. This phenomenon is true also in hypergraph. This is a result by Erdős, that if you have a k-uniform graph, so now the edges have size k, and you have a positive proportion of all the positive edges, then you also get a blow-up of an edge, which is kind of a complete k-partite graph. Okay? And let me also say that in both of these theorems, the size of the blow-up that you can ensure is logarithmic in N, polylogarithmic in N, and the specific constants appearing in front of this polylog and also the exponent depend on k and many other things, but this is also a very interesting question trying to optimize these dependencies. Okay, so this is something that we know for fixed copies of a fixed graph, and a question that you can ask is, do we get something similar instead of thinking of small graphs, do we get something for spanning graphs? Okay, so for instance, this is a classic theorem, Dirac. You have a vertex, graph with n vertices, and the minimum degree is above n over 2. Then you have a Hamilton cycle. So then I can ask, if I have a minimum degree which is slightly larger than what I need for the Hamilton cycle, do you get spanning structures which are more complicated than a Hamilton cycle? Do I get something else from this extra minimum degree condition than do I get? And something like this is true, but you have to say which kind of structures you can get, and some of the ways you can make sure how to analyze the copies that you get is that you need to understand a little bit about which kind of complexity do you get from these structures. This is what we're going to say now. So something that we know in a slightly different setting, but also very related, if you have n-vertex graphs with minimum degree larger than t minus 1 n over t, and a little bit more, then something that we knew is that you contain clique tilings. So in this case, triangle tilings is a spanning collection of triangles covering every vertex. And I use this example here because I want to illustrate this phenomenon that not only you start to get these tilings, but you start to get more complicated structure based in this kind of triangle shape. So first we knew that we got tilings. Then using the same minimum degree threshold, we know that we get the corresponding powers of Hamilton cycles. So it is a power of a Hamilton cycle is that you get a cycle, and then you start adding a little bit more edges. You have to add the edges at distance at most t in this cycle. Or other ways you can think of this structure is that you have a collection of triangles that you are pasting together in a cyclic way, right? So you have a triangle, then you paste next to it other triangle, other triangle, other triangle, and you do something like this until you get a spanning structure with n vertices, okay? And then, after this, we know something which is much stronger, which contains all of these results, is that you actually get any graph which has bounded degree, is k-colorable, and has sublinear bandwidth, okay? So this is kind of very general theorem. This is called the bandwidth theorem by Bocher, Chak, Taras. And I want to explain a little bit what does this theorem say, because it's very important to what I want to emphasize here. So I should begin by saying what is bandwidth. So for a graph, you say that the bandwidth is at most b if you can order the vertices, label them in a line, and so that you get that the longest edge in this ordering has length at most b. So if you have a cycle, you can do something like this, and you have this very long edge. So this is not a very good way of ordering this graph. But you can also do something like this. This is much more clever, because in this way, you get that every edge has length at most 2. So in this case, you can see that the cycle has bandwidth at most 2, and every cycle has this bandwidth at most 2. So in some sense, it's a measure of complexity of this graph, okay? So this is bandwidth. This is the theorem, the bandwidth theorem, which says the following. This is the statement. So if you have C and N, 1 over N small enough, compared with the other parameters, then every time you have an n-vertex graph and the correct minimum degree condition, then you contain every graph with bounded maximum degree, chromatic number at most t, and this bandwidth, which is sublinear, smaller than this c times n. Okay? So you get this whole family of spanning subgraphs, not just cycles, but also these funny graphs, which can be very wild in shape, right? So maybe I should say that it has a lot of consequences, because you have many graphs which you can study using this kind which satisfy this type of characteristics. So for instance, if you apply this theorem for t equals 2, you are thinking about 2 colorable graphs. So for instance, this theorem will imply that for this minimum degree condition, which is 1 over 2, you will get all spanning bounded degree trees, for instance, because they're bipartite, 2 colorable. Some nice consequence as well, if you use this for t equals 4, then you get all bounded degree spanning planar graphs, because they are 4 colorable, we know. And also you can prove that they satisfy this bandwidth condition as well, if they have bounded degree. And you get all possible copies of tilings with this, and et cetera, et cetera. You can also prove that there are various measures of complexity of graphs, such as tree width and expansion and blah, 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 which you can show they are somehow equivalent under this bounded degree condition. So in fact, this gives you a whole big family of graphs which you can embed using this kind of theorem. Okay, so this is the bandwidth theorem, and I want to summarize. This is, in essence, what we have. So in your graph, if you have the minimum degree so large that you get the power of a cycle, then you also get this bounded degree, t-colorable, low complexity graph inside, spanning subgraphs inside your graph, okay? So this is what we have. And I want to extend this to hypergraphs. And if I want to extend this to hypergraphs, I need to say something about all of the definitions which I told you about, because it might not be clear what is bandwidth in a hypergraph, what is minimum degree in a hypergraph, and what is a cycle in a hypergraph. So I will tell you all about this. And let me begin with bandwidth, because the notion of bandwidth that we use, it is essence equivalent to the other one, but we do measure in a little bit different way. So I want to emphasize this. I want to explain carefully. So some observation is that if you have a blow-up of a path, let's say a B blow-up of the power of a path. So I have this square path here, collection of triangles spaced together. I have the B blow-up, so every vertex is now B vertices. And I have a subgraph of this. Just from this information, I can bound the bandwidth of this graph. I will need to order the vertices in some way so that no edge is longer than at most BT. And this is easy to do because I will just follow the order given by this cluster. I will just put the first one, then the second, and the third, and you can check that the no edge will be very long by doing this. Okay? So I hope this is clear. And something that is also interesting is that you have a sort of converse to this statement, because you have a graph which has bandwidth B, and it's partite or colorable, if you want, then you are a subgraph of the blow-up of a power of a path. So I want to compare both things, low bandwidth with being a subgraph of the power of the blow-up of the power of a path. Okay? So I will give you some ideas of how can you prove this using this example here. So this is a graph with bandwidth at most 3, so no edge is longer than 3. And this is 3 colorable as well, so I have a coloring like this. And the idea, I need to make sure that this is a subgraph of the blow-up of a power of a path. So I need to group these vertices into clusters so that they belong to some blow-up of the power of a path. The strategy to do this is that you can separate the vertices according to your ordering, which is the bandwidth ordering. So you use these intervals of length b. By doing this, notice that I can have edges between 2 consecutive intervals, but I can never have an edge between this interval and this interval, say, because it will be too long. So you have this. And I will use the colors, given my coloring here, so I have these 3 colors. I will give numbers to these colors. And the way I do this is that I have to group these blocks together in a funny way, in a coherent way. And this is not so difficult to do. I look at the first interval. I have colors, vertices with colors 1 and 2, so I just put them together like this. In the second interval, I have blocks of color 3, 2, 1. What I do is that I will put them next to them, but I'm starting with color 2. So I will put the block first of color 2, then 3, then 1. And I will do this cyclic shift of assignment of these colors here. So then in the next block, I will put the vertices of color starting by 2, then 3, then 1. So it will be like this, through, then 1, then 2, sorry. And then in the next one, I will start by 1. So I have 1, then 2, then 3. OK. So this will be my blocks. And these blocks here, this is the graph that I get. And I claim that this is contained in the blow-up of a power of a path, the square path, right? And this, the condition that we get this from this coloring ensures that each one of these kind of macro blocks here is an independent set, so this is fine. And also this has the correct edges here. So this shows that these 2 notions have this kind of a relationship between each other. And so we will use this. So instead of defining bandwidth for hypergraphs, what I will want to do is that I will want to find spanning k-graphs, which are subgraphs of the blow-ups of powers of path. Okay? And this is something that you can do by analyzing the graphs in this way. It gives a much more cleaner way to state our results. Okay. So then I need to talk a little bit about cycles in hypergraphs. But before this, I need to talk a little about degrees. So in graphs, it's very easy to define minimum degree. But in hypergraphs, you have many different possibilities for the degree, because your edges have size k. So depending on what you're measuring, you have many different possibilities. So usually we have many types of possible different degrees. So you can select any number between 1 and k minus 1. You will look at sets of size d, and what you will do is to count for this set S how many edges of size k contain this set. So the number of edges which contain S is what we call the degree of S. And if this set has size d, you can see that this is a number which is at most n minus d, k minus d, because this is kind of all the possible ways to complete this set to a set of size k. And this clarifies this definition over here. So you pick a number between 1 and k minus 1. This is d. You will look at every set of size d. This gives you, you take the minimum of them all, and then you divide by this n minus d, k minus d. This normalized, and this will give you a number between 0 and 1, okay? And something that you can also check is that you have all of these chain of inequalities that this minimum degree condition satisfy, and this also kind of explain why it's easier to obtain results when you control this type of minimum degree condition, because if you have a lower bound on this value here, all of the other degrees are also lower bounded. But if you only control, say, the minimum 1 degree, this could be 0, and this gives you less information in general, right? So usually we know much more results when d is large, very close to k, and not so many results when d is very small. Okay. So this is the minimum degree. I need to define the power of cycles. And the way I like to define powers of cycles is just as before. I will take cliques, and I will paste the cliques together in a cyclic way. So I will define the t minus k plus 1 power of a cycle by joining t cliques in a cyclic fashion. So if I look at the 1 powers, this will be just a cycle. In k uniform graphs, what I will get is just an edge. I need to paste copies of this edge together in a cyclic way. So this is the first edge. Then I get second edge, third edge, etc. So this will be, if you do this and then you close this will give what you get as a Hamilton cycle, right? Some people will call this a tight Hamilton cycles because there are other ways to define cycles, but this is the only type of cycles which are interested here now, okay? So this is a cycle in a k-uniform graph, and the power of a cycle then will be something a little bit more complicated. So for instance, in 3-uniform graph, if you look at the 2 power of a cycle, what you will need is a clique of size 4, that tetrahedron, and you will need to paste copies of this tetrahedron in this cyclic way. So this is the first, this is the second, and then becomes super messy, but this is the finish. And so this is the power of a cycle, and I want Hamilton cycles, so use this structure with n vertices, and then you can define what we call this threshold or the extremal parameter, this fdktn. So what is this? So for every graph on n vertices, you maximize the minimum degree over all graphs which do not contain this copy of cycles. Similar to the extremal number of a copy of a given graph, you want to maximize the d degree, okay? And in my situation, I don't really care about n, so I will just take the lim sup, let n tend to infinity, and I will say that this is the threshold. I'm interested in this threshold for the existence of the power of a Hamilton cycle. So I have removed at least one of the parameters, but I still need to deal with 3 parameters. And just to clarify, so k is the uniformity, t is what is the size of the cliques which I am pasting together, and d is what is the degree which I control in my k-uniform hypergraph. Okay? So this is the threshold for the power of a cycle. So I don't know if there's questions or. Yes, this is also possible to define it in this way. Yes, it's equivalent. Okay, so what do we know about these thresholds? So we have saw this result by Dirac, where every graph with minimum degree n over 2 contains a Hamilton cycle, and then you can check that this implies this equality, right? Because then n over 2, you divide by n. I only care about this constant, which is between 0 and 1. And here I'm telling you that 1 degree in 2 uniform hypergraphs gives you Hamilton cycle. This is basic. So then something which is more recent is that we knew how to get this for hypergraphs, for tight cycles, for k minus 1 conditions in the degree. This is the result of Rodel-Rushinsky and Semeredi. And in the last few years, there have been some advances are making this d even smaller. So from k minus 1 to k minus 2, k minus 3, etc. This is what we know so far. So for instance, for k minus 2, we know that this threshold is 5 over 9. And this is actually for every k. This is for every k which is at least 3. And this is a result by Paulsen, Ryer, Rodel, Schulke, and also independently by Richard Lang and myself. And very recently, we also knew how to do this for k minus 3 degrees, okay? And essentially, this is all we know with equality. Every time you decrease the value of d, this problem becomes significantly more harder. So this is essentially all we can do with the current technology at this point, okay? But we know some bounds. We got some general bound. This is a result by Richard Lang and myself. So if you give me any k, sorry, this t should be 1. This is not for power of cycles, but just for normal tight cycles. But you can do for any k and any d, you can prove this upper bound, which depends on this difference, which is k minus d. And kind of explain the difference why when you make this k minus d to be larger, so d to be smaller with k fixed, the problem becomes much more difficult. This threshold, actually you can show that it also has a lower bound which tends to 1 when k minus d goes to infinity. So you have a very nasty structure here. And for powers of cycles, there's this result for graphs. This already appeared in the screen. This is that for the t minus 1 over t times n, you get this t powers of cycles. This is for graphs. And for hypergraphs, we don't know any exact result. There's this result for 3 uniform graphs and squared cycles. There's a bound of 4 over 5. For general k and t, but d fixed to k minus 1, we also have this bound, which is by myself together with Matthias and Maya Stein. Okay? So this is a kind of a summary to what we know about these cycles. There are a few exact results, all of them with d being very close to k. And for powers of cycles, not so much. Okay? But anyway, I would like some statement like this. So in graphs, we know that if we are above the minimum degree threshold, which gives you a power of Hamilton cycles, then you get all of these other graphs, which are spanning, bounded degree, bounded bandwidth. Okay? So then I would like something like this. If you have n vertex k graph, and your minimum d degree is above what you ensures the Hamilton cycle, or the power of Hamilton cycle, and a little bit more, then you should also contain all the spanning subgraphs, which are blow-ups of the power of a Hamilton cycle, because we saw this is kind of equivalent to having this bounded bandwidth condition. And this is true for the graph case, when the edges have size 2, and this m is a constant. This constant here is required because their theorem requires bounded maximum degree. Otherwise, you will not have such a statement. But this is true, at least in this case, by the bandwidth theorem for graphs. So maybe this is true in general. The fact is that we don't know how to prove this in general. So working with this in graphs which satisfy this condition, just having a power of cycle or having a Hamilton cycle is a very weak condition. It doesn't give you much freedom to work with. But we have something similar, which is also very informative, that we can do something like this as well. So instead of Hamilton cycles, I will work with a new structure, which I call the framework. So the first thing I need to explain here is that if I want to work with powers of Hamilton cycles, so let's say k uniform, and I am interested in this t minus k plus 1 power, is this collection of clique of size t next to another clique of size t next to another clique of size t, blah, blah, blah. So equivalently, I could define the hypergraph where every clique of size t is an edge, and just look for a cycle in this new graph, right? So I will consider this graph, which I call ht, and I will look for cycles and connected structures in this auxiliary hypergraph. This is a T uniform hypergraph. And I define the following. So I'm saying a subgraph is a KT framework if I can find a subgraph in this auxiliary graph. And I will need 3 properties, which are very important. The first one is that you need to be tightly connected. Tightly connected means, I mean, you say that 2 edges are tightly connected. They have size t, and they need to intersect in t minus 1 vertices. And if you can, this will define that one edge connect to the next one, but then you can repeat this and go from one edge to another. If you can go from every edge to every other edge, you say the graph is tightly connected. And this is a natural property to have, because if you look at a cycle, the cycle is tightly connected. So this is also a kind of necessary condition. Something else that is very important if you want a Hamilton cycle is that you need some space condition. So a Hamilton cycle in a graph with an even number of vertices also contains a perfect matching. And in general, if you have a tight cycle like this, and you look at edges in this way, so I look at the first edge, then I go to the next one, and blah, 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 you also get a perfect matching. In general, because of divisibility conditions, maybe you don't have a perfect matching, but you also always have a fractional perfect matching. So this is my space condition. And again, this is a very natural condition to ask, because every cycle contains a fractional perfect matching. I will also ask for two other conditions, which are less natural, but not so much. I will ask that my framework contains a cycle of odd length. By odd length here, this is not the correct word here, but I need a cycle such that the length is not divisible by t. Actually, one coprime, it should be coprime with t. But I also think it's a natural condition, because if I am working in the threshold for getting a Hamilton cycle, I should get this cycle no matter the number of vertices of my graph. So if I want to find my graph even if the number of vertices is not divisible by t or coprime with t, if I have a Hamilton cycle for such values of t, then I do get a cycle with this property. So this is also a very natural property to ask. And I should say there are some other conditions which I ask, which I will not write here because they're a little bit more difficult to motivate. But maybe at the end of the talk, I can explain how they come into the proof of this. But at least these three properties are very natural, and you could say they're necessary to have this Hamilton cycle. So I will define a threshold for the existence of frameworks. So again, yes, there's a question.
What's K?
Sorry?
What K means in this definition?
K, because I have a graph H, which is K uniform, but I want to work with t minus k plus 1 power of cycles. So I have two parameters, k and t. So k is the uniformity of the original graph, and t is the uniformity of the second graph. Okay? Right. So I can define the threshold for the existence of frameworks, which essentially will mean if the d degree of my k graph is larger than this new parameter, then I will get a different structure, which is a framework. Okay? So this is what we define. And we define this because it seems easy for us to work with this kind of different structure than a Hamilton cycle. We could prove with Richard Lang and myself that no matter your choices of t, k, and d, you get this inequality, which, what does this say, is that essentially if your minimum degree condition ensures you the existence of a framework, then you also get the existence of a corresponding power of Hamilton cycle. And the conditions I told you about this framework are somehow the necessary ones. So this connectivity, the matching, and blah, blah. So we like to think of this result as saying that the necessary conditions are essentially sufficient, okay, to get this Hamilton cycle. So we have this property for this new parameter. And the framework, or having the minimum degree, which ensures you the existence of a framework, will also give you the corresponding power of Hamilton cycle. And in addition, we can also show that in every single case where we know some bounds for the Hamiltonicity threshold, we also know the same bound for a framework threshold. So we don't know any case where these two values are different. Okay? So this gives some evidence, at least, that they should be very close together in any case. So this is, I just took every inequality from the previous slide and added an asterisk to get these inequalities here. I should say that these inequalities here are not automatic from the definition. You have to work a little to get them, but actually not so much in general, because if you look at the proofs of all of these Hamilton cycle results, much of the proofs work actually by finding the matching, by finding connectivity. So it's also not automatic, but most of the cases is very easy for them using what we know already. So every bound that we know for Hamilton cycles and powers of Hamilton cycles, we also do get for this framework result, which is the new parameter here. Yes?
Just to get at that, so the back of the theorem says, since it's the power of
something like that. But here you are comparing the framework with the Hamilton cycle or power Hamilton cycle. And we don't know if there's actually a difference between them because it has these mostly necessary conditions. We believe they are essentially the same, but yeah. Okay, and okay, this is for powers of Hamilton cycles. But then something that, this is what we call what I like to say, this is our version of the bandwidth theorem, is that if you have a graph where the minimum d degree is slightly larger than this parameter, so this is not the power of cycles parameter, but the framework parameter, then you do contain all the spanning subgraphs, which are blow-ups of the power of a Hamilton cycle, okay? And something I want to emphasize about this theorem is that here the blow-ups are not of constant size, okay? So here we can take the size of this blow-up to be of size even of poly log n, okay? So this is the main result. And I also say that if you are in the very particular case of graphs, where k equals 2, then you can also improve this m to log n, okay? To poly log n, actually, to something like that. Okay, so this is what I say. This is the bandwidth theorem, and again, I want to summarize the minimum degree condition, which gives you framework. Not only gives you the power of Hamilton cycle, but also gives you the whole family of graphs, which I told you this is kind of the similar low complexity graphs, which belong to a blow-up of a power of Hamilton cycle. Okay.
So could you specialize this to the case of graphs and say what it means?
Yes. So for the case of graphs, so in the simplest case in graphs, you can say that if you have a graph with minimum degree a little bit more than a half, so this is the threshold for Hamilton cycle, and we say not only you get a Hamilton cycle, but you get a spanning M blow-up of a cycle with clusters of size log n. Okay? This is kind of the easiest case for graphs and minimum degree conditions.
And now that I interrupted you, I'm sorry. So in the previous slide, you had the star quantities, right?
Yes.
What does it mean if the second thing, t, is 1? Because then it's some...
Yeah, so 1 is just one power of a cycle, just tight cycle in general. So cycle in the case of graphs?
T minus k plus 1?
Yes.
No power.
It's no power. It's that you have to do this shifting by k because I want cliques of size t.
But k, right.
Yeah. Is there other questions? Yes. No, this is the correct one, because this is the d degree. So you look at sets of size d, and you look at the degree, how many ways you can complete it to an edge of size k. So you have n minus d other vertices, and you can choose sets of size k minus d. Yes. Yeah. So I don't know if there's other questions or yes. Okay, I will just say, I was just going to say this. So this is our theorem, and I want to compare with this bandwidth theory. It's not comparable with the bandwidth theorem because, so I would say our theorem is stronger in some sense and weaker in the other sense. It is stronger in that we do not require any bound on maximum degree. They do require a bound on maximum degree because the techniques that they use regularity, blow-up lemma, this kind of requires something like that. And in particular, it means that we can embed families of graphs where the number of edges is not linear. It can grow as n poly log edges. But it's also weaker in some sense than the bandwidth theorem because our bandwidth is controlled by this poly log factor, and they can do bandwidth which is even sublinear, right? So this is you gain something and you lose something by doing this. Okay. Okay, so something else I want to say. So I told you this result about minimum degree conditions, which is a most natural one maybe. But I want to say that this also, with the same proof, works in other settings that people have studied. So for, let's say, Hamilton cycle, people have done all of these things about degree sequences or sum of degrees and pseudo-random conditions, etc. And in our case, our proof can still say something. This is for dense graphs only, so not for sparse. But you can say something if graphs have some kind of uniformly dense graph, for degree sequence, and blah, blah, blah. So we can also get automatically many results in this other type of settings, which are not exactly minimum degree condition, but something different. And we can also get the results, and in many cases, we know the result for Hamilton cycles, and our result will improve this to this bandwidth result. And okay, and I want to say that our proof doesn't use regularity lemma of any kind, and also doesn't use absorption. I mean, you don't have to know what is this, but let me just say that these are very natural tools for working with spanning structures in graphs, especially regularity lemma, and it's the oldest one, absorption a little bit more modern, but we don't use any of those things, so we really use a new method to prove this kind of result, okay? And, okay, so in the last part, I want to say something about the proof, and to tell you something about the proof, I will need to make some definition, and so I have a k-graph H, and given S, which is an integer, and for any hypergraph property, I can define the property S-graph as this, which means the following. It means that I will have my hypergraph H, like here. I am given a number S, and every time there's a subgraph of H of S vertices satisfying the property, I will put an edge. So this is an S uniform graph which tracks in which part of the graph I do get my property. So which kind of properties I am interested is, for instance, this is just an example, but in general, you could ask that this, I don't know, maybe the large subgraph has minimum degree more than a half, and maybe ask also in the small graph, I also preserve some kind of minimum degree condition, okay? So this is the subgraph. This is the tool that we use. And what we need for the proof to work is the property of having a framework, okay? So every time you have some condition which implies the existence of a framework, then we will have to work. This is the kind of the more technical condition that we need, is that this graph, this property hypergraph, has very large minimum degree. So not all properties will satisfy this, but if you have some very large minimum degree condition, and you can do a probabilistic argument, randomly sample a set of S vertices, you can show that with large probability, this property is also inherited by these small sets, right? So in this, you can prove, and this is a consequence of concentration inequalities, that if you have, let's say, a graph with minimum degree more than epsilon, then for S, you will have the minimum degree of this uniform hypergraph for this property more than, you have some error, but this some error that depends on S, okay? And this is for this S uniform hypergraph, so you get something like this. And again, this is a consequence of concentration inequalities, but you can also use similar method to work with other properties, not only minimum degree properties, but also, for instance, this kind of uniform density properties. If you know what that is, you can also show that this is also inherited by small size sets or something like that. So it gives you some flexibility. It's not only for minimum degree conditions. It's for every property that satisfies this kind of inheritance property. Okay? Okay, so this is my graph. I have my auxiliary graph. What do I do with my graph? If this S uniform graph has very large minimum degree, and now I am talking in the S uniform world, because this is my S uniform auxiliary hypergraph. Some properties that, okay, the minimum, very large minimum degree conditions implies that I can find a perfect matching in this auxiliary hypergraph. So not only I will get just one edge with this property, but more generally, I could get something like a tiling, like this. So this is something you can show that it is true. Actually, I will want a little bit stronger. Not only I want perfect tiling, but I will want almost tiling, not with copies of edges in this graph, but I will like to have a tiling with blowups of edges, okay? And this is also, you can also show that this is a consequence of just having large enough minimum degree in this hypergraph. So not only a matching, but I will get H and a collection of blowups. And each one of these blowups will be a complete blowup in this S-uniform world. And you can show that the size of this blowup is poly log, essentially. So I can almost cover the graph with blowups of this S-uniform hypergraph. Okay? Yeah, and we use this result of Erdos to actually get this kind of blowup. This is what I showed in the first slide, that you can, this supersaturation is true for dense hypergraphs. Right? So this is an almost blowup. I want a spanning structure. It turns out that you can cover some remaining vertices by adding extra blowups on top of them. You can do this in a kind of greedy way. And what you will get is a collection of blowups, which you can make vertex disjoint by removing vertices if they are in the intersection or not. And you can connect the blowups with other blowups. And again, this will be a property of this auxiliary hypergraph having a very, very large minimum degree. So, then what you will do with these blowups is that, okay, so we don't use regularity, but essentially, these blowups will, you can make sure that these blowups will look like a blown out copy of some reduced graph. Because what happens for our property is we want this property to satisfy the property of having a framework. So you will have some subgraph which you have blown up, and you have a perfect matching in this blowout. You have a connectivity, blah, blah, blah. And if you know some regularity proof, you will know that having these properties in a reduced graph will allow you to find a large structure like a cycle in your graph. In this case, we have something even stronger because we have a complete blowup. So we can embed however we want. We don't have to care too much about the embedding inside these blowups because they are complete. Okay? So this gives you a very strong tool to embed this kind of graphs. You have to be careful with how you do the embedding. This is more careful. I will not go to these details.
So just to see if I understood right, if you have a set of size S, for example, and you build a path there, and you
Yes.
can go to another set of size S in the same blowup because they are in the same.
Yes. Actually, there's one step which I didn't say. But when you look at these blowups, I mean, because the only property of this S-uniform hypergraph is that the induced graph has some, let's say, large minimum degree. But they could be different graphs, of course, right? You can do some previous like cleaning steps, so you can make, in your blowups, you can ensure that they're copies of the same isomorphic graph, okay? So they will actually be like a blown up cover of the same graph. And as you say, then you can go from one copy of this graph to another if you can connect them carefully. And actually, I should say maybe the property of this framework, which I didn't say before, is precisely the property that allows you to go from one copy to the other one, which is not given by this. But yeah, you need this property for this. Another question? Yes?
Is it possible to illustrate this with a simple example to illustrate it, say, for graphs, having this like
Yes, I can try. So if you have graphs, then what you will do is to find this kind of almost spanning blow-up cover, which you can make spanning. So I will just assume it's spanning. So then you will find collections of blow-up like this. And remember that each one of these, you have S clusters because it's a blow-up of a S uniform edge. But each edge in this graph corresponds to a subgraph of H, which has, let's say, large minimum degree. So I have some kind of reduced graph here. And is this reduced graph, what do I get? Because I am interested in saying Hamilton cycles, the framework property implies that I have a perfect matching here, which is also connected, or something like this. But then I get this structure in H. And this is a blow-up, which is a complete blow-up. And then I can easily allocate a cycle here. You will do similarly as you do in a regularity proof here. You can allocate a long path.
Sorry, how much is S? Is S constant?
It is constant. Yes. And the blow-ups here have size logarithmic. Okay. And you have another copy where you do something similar. And then you will have another copy on top of this one, which allows you to make the connections between one and the other. Yeah. Is there other questions?
That picture is very disconnected, right? So you have
Yes, I didn't add the connections to this. Okay. What you do need is another round of this blow-up cover, where you will actually take 2 blow-ups and add a new one. And actually, I'm not saying the full details here because it's even more complicated than this. But you need to work with a different uniformity. So you have S, and you have some S2, which allows you to find a new blow-up which connects the 2 one. But this new blow-up would also be an instance of this kind of reduced graph, which you can use to go from one to the other. But this is a structure which you add on top of this spanning structure. So you first find this one, and then you add the connections. Mm-hmm. Yeah. There are more questions? No. OK. So yeah, this is what I wanted to say about the proof. So let me just finish with a few possible directions for the future. So everything, I mean, if you know what cycles in hypergraphs, you will know that I say everything for tight cycles. But you can try to work with different types of cycles, like loose cycles. And for this, it's also interesting to find frameworks, because we're also interested in determining what thresholds would give you a loose cycle. So a loose cycle is like, let's say, for 3 uniform. Instead of insisting that every 2 consecutive edges intersect in 2 vertices, maybe they intersect in less than edges. So this will be an instance of a loose cycle in 3 uniform hypergraph, right? We still don't know all the thresholds for loose cycles, but with future work with Richard Lang, we can also give you frameworks for loose cycles. This will allow us to determine many new thresholds for loose cycles which are not known yet, and also improve this to some kind of blow-up version of these results. Something that's also could be interesting is that we get these blow-ups of size poly log log n. This comes in some part in our proof actually having to do with this connectivity condition where we know this log log. Maybe it's possible that even polylog is true. Polylog will be best possible because of random graphs. A random graphs, you will not get a complete bipartite graph with more than log n vertices. This is something that is a natural bound for the best that you could get. But we get polylog log n, and maybe polylog n is true. And also, it could be interesting to think how to extend our proof to embed other type of graphs. So for instance, I said that the bandwidth theorem gives you the embedding of all bounded degree trees. For instance, this is a structure which has, you can prove that have bandwidth of the order n over log n. You can also define hypertrees, of course, and they have bounded degree, but they do not have bandwidth which is polylog log n. They have bandwidth which is more larger than much closer to n. So our proof doesn't give you the embedding of all bounded degree hypertrees, but they also have some kind of different nice structure, and we do have some results for spanning hypertrees. So it could be interesting to see how our proof could be modified to deal with other measures of simplicity of the graph, such as hypertrees. They should also be possible that some general tool will allow you to give you the embedding of this other type of graphs. About the specific thresholds, the smallest open case is this. This is for 3 uniform graphs and the squared of a cycle. And we don't know what's the answer. I believe it's 3 over 4 because the lower bound construction is very natural. The only thing we know is that between 3 over 4 and 4 over 5. And determining this will be very interesting because if we know this for the framework, this will also give you all of these 4 colorable, because of our result, it will give you all of this family as well. So determining thresholds for powers or Hamilton cycles is a very natural open question, and this is the smallest open case, and we should know what is the value of this specific one. And I should finish with this question. So we have defined this new structure, which is our framework, which is very useful to work with. We know that in every case where we have a bound for the Hamilton cycle, we do get equality. So I don't know of any example where this equality doesn't hold. I should believe that it always holds, but I don't know how to prove it. This should also be very interesting to know if this is true or not, because we believe our framework it's a very natural way to summarize all of the necessary properties of the Hamilton cycles, but we still don't know. We are missing some information on how to prove this equality, and we believe this should be very, very interesting. Okay? This is all I wanted to say, so thank you very much.